All right, welcome to part 2 of our electron configuration discussion. We're going to now address orbital diagrams, which will provide us even more information about electron configuration for each element, and more importantly, it will allow us to intelligently discuss exceptions, or rather deceptions, when it comes to electron configurations. Because really there aren't exceptions, they're just things that we can't predict from the periodic chart alone. So let's start by taking a look at what an orbital diagram is. This drawing that I've done several times for you is what's known as an orbital diagram. An orbital diagram can be written like this, or you can actually write it all in one line here. Come on, shrink for me. If I wanted to, I could write an orbital diagram as well, just in one line. 1s, 2s, 2p, 3s, etc., etc., etc. Now, when we write an orbital diagram, each one of these boxes represents an orbital. And I like boxes. Your book, however, actually uses a format that I like as well, and it's actually an easier format to use when you get into more complex molecular diagrams, and they represent orbitals using a line. So they would say 1s, 2s, 1, 2, 3, right? Because you have 3p orbitals, 2p, and then another line for your 3s. So you can represent orbitals using either boxes or lines when you're doing your orbital diagrams, and you can write them in order of increasing energy like I did over here, or you can write them linearly. And you can also use noble gas notation for them, but let's do one thing at a time. Orbital gas notation represents orbitals using boxes. It represents electrons using arrows. The electrons' arrows can be either pointing down or pointing up. Let's start by filling out an orbital diagram for an element, and let's start with a fairly simple one. Let's do an orbital diagram for helium. Helium's in the first row, so it's first energy level, and helium, remember we said, belongs in the s block. How many electrons does helium have? Helium has 2 electrons. We need to place our electrons in that orbital, because each orbital can, remember, every orbital holds 2 electrons. So now we want to draw arrows to represent our electrons. When we draw the arrow for an electron as either up or down, we're representing what's known as the electron's spin. The electron's spin is exactly what it sounds like. The electron's spin is which direction it rotates, or which direction it aligns itself with in the presence of a magnetic field. And there's only 2 ways an electron can align itself with or rotate with in the presence of a magnetic field. It can either rotate clockwise or it can rotate counterclockwise. So we have 2 spins to represent. One rotates up, one rotates down. According to Pauli and our Pauli exclusion principle, we have the Pauli exclusion principle that states an orbital can only have 2 electrons, and that electrons occupying the same orbital have to have opposite spins. Matter of fact, it goes on beyond that. There's even, it was just published in Journal Nature a couple months ago that when you create a new particle from energy, that spin neutrality of the entire universe has to be preserved. So if you create 2 particles from energy, those 2 particles created will have opposite spins. Not only that, but you can separate them by miles, and they will maintain that spin opposition. But that's beside the point. For electrons in the same orbital, they have to have opposite spins. This is known as Pauli's exclusion principle. So that means that if we have 2 electrons for helium, those 2 electrons have to, and they're going to occupy the same orbital, those 2 electrons occupying the same orbital are going to have opposite spins. So we would write an arrow pointing up and an arrow pointing down for our helium. So that's the orbital diagram for helium. Chemistry's easy, life is hard. Let's kick it up a notch. Not to bore you, but let's go to boron. You've located boron on your periodic table, I hope. Boron's the first element in the 2p block, right? So we're going to read our entire periodic table to get to boron. If we were to write boron's condensed notation, we would say that boron is 1s2, 2s2, 2p1. To translate that into an orbital diagram, we have 2 electrons in the 1s, so we're going to have to draw 2 arrows pointing opposite directions. Then we have 2 electrons in the 2s, so we're going to draw 2 arrows pointing in the opposite direction. Then we have the 2p. The 2p has 3 orbitals that are degenerate, meaning they have the same energy. And we have 1 electron to place in it, so we're going to place 1 electron there. Chemistry's easy, life is hard, yes? Also, it doesn't matter if you put that arrow up or down. Most people are positive people, so they always tend to draw that lonely arrow pointing up. Let's keep a good thing going. Let's take a look at carbon. Carbon, when we write its condensed notation, 1s2, 2s2, 2p2. So if we're going to draw the orbital diagram for carbon, I'm going to write 1s, 1 2s orbital, and then I'm in the 2p, and the p has 3 orbitals, 1, 2, 3. My carbon has 2 electrons in the 1s, so 2 arrows pointing opposite direction because of Pauli. Then I come to the 2s, so I'm going to have 2 electrons pointing the opposite direction because of Pauli. And now I have 2 electrons in my 2p. I have multiple options for what to do with them. I could draw 2 arrows like that, or I could draw 2 arrows like that, or I could draw 2 arrows like that. Which is the right way to do it? If only we had a rule to give us some direction. Sure enough, we have a rule to give us direction, and it's called Hund's rule. It says if 2 or more degenerate orbitals are available, in other words, if we're looking at our carbon example, If 2 or more degenerate orbitals are available, we've got 3 degenerate orbitals here. 1, 2, 3. All 3 have equal energy. So if 2 or more degenerate orbitals are available, 1 electron goes into each until all are half full. Not only that, the electrons in the half-filled orbitals all have to have the same spin. I like to call this the roommate strict zoning ordinance. In other words, first of all, if it costs the same energy, and that's what degenerate means, for an electron to live without a roommate as it does for an electron to live with a roommate, what is it going to choose? It's going to choose to live without the roommate, right? Trust me, if you don't think that's the correct answer, you've never lived with a person for a prolonged period of time. So you've got the 2 electrons that are going, you have 3 degenerate orbitals, so the 2 electrons are each going to have their same orbital before they double up. Since it's the same amount of energy to go here, to have 2 electrons here as it is to have 2 electrons separately, the 2 electrons are going to want to live apart. Next, they live in a neighborhood with a really strict zoning code. Everybody has to have the same mailbox. So that means that these 2 electrons have to have the same spin. That's what Hund's rule is telling us. So this is the only allowable, acceptable orbital diagram for carbon, with these 2 2p electrons in separate orbitals facing the same direction in terms of their spin. Let's take a look at another. This time, let's take a look at phosphorus. If I write the condensed notation for phosphorus, the preceding noble gas is neon, and I read down, I've got 3s2, 3p3. Phosphorus is the 3rd element in there. Okay, if I were to write it out longhand, 1s2, 2s2, 2p6, 3s2, 3p3. I can write my orbital diagrams for phosphorus using noble gas notation and the long way. So you can use noble gas notation for orbital diagrams as well. I can write my phosphorus orbital diagram as either neon 3s, 1, 2, 3, 3p, or I can write it 1s, 2s, 2p, whoops, being ahead of myself there, 3s, 1, 2, 3, 3p. Let's do the orbital diagram notation first. Two in the 3s, any 2 electrons that share the same orbital have to have opposite spins. Then I have 3 in the 3p. Hun says electrons don't want to have a roommate when it costs the same amount of energy to live in an orbital. So all my 3p orbitals have the same energy. So an electron is going to move into each of those orbitals before they double back up. And those spins all have to point the same direction. So that would be the electron configuration for phosphorus if I wrote it out the long way. But once again, I can save time by representing my boring core electrons that don't do anything chemically using my noble gas notation. Chemistry's easy, life is hard, yes? Let's do another one so that we begin to encounter a slightly new scenario. Let's look at chlorine. I'm going green since it's chlorine. Chlorine, if I was to write its condensed electron configuration, we'd have neon then we'd have 3s2, 3p5. So its orbital diagram would have to be neon, 3s, 1, 2, 3, 3p orbitals, 2 electrons in my 3s2, so 2 arrows pointing opposite directions, 5 electrons in my 3p. These 3p orbitals all have the same energy, so I'm going to place 1 electron in each before I double back. I'm now out of empty orbitals, so now I have to double back and share. So that's 5 electrons in my 3p, so I'm good, right? Chemistry is easy, life is hard. Let's kick it up a notch. Let's take a look at something in the D here. Let's take a look at... Alright, let's kick our orbital diagrams up a notch. And let's do technetium. Hello, I'm right here, number 43. Alright, first we find the preceding noble gas krypton. Staple brackets, and then we're going to set up our orbital diagrams. So we're one, 2, isn't technology great? 3, 4, 5 down. S block, so 5s. Then we enter the D block, and this is the 4D. Remember, D block is row number -1, and a D has 5 orbitals. S1 orbital, P3 orbitals, D 5 orbitals. So 1, 2, 3, 4, 5. 4D. The S is completely filled. And then where's technetium in the D block? It's 1, 2, 3, 4, 5 in, so it's 5D. So we're going to place 1 electron in every orbital until they're filled up. 1, 2, 3, 4, 5. Ta-da! Chemistry is easy, life is hard, yes? Let's do just one more. Let's do something that we're going to walk on the wild side for. Let's do let's do this guy down here. All right. First thing we're going to have to do is we're going to have to find that preceding noble gas, and we're going to have to work to do that. Our preceding noble gas, we're at 60 here. So 59, 57, 56, 55, 54. So xenon is our preceding noble gas. So we read forward from xenon. 1, 2, 3, 4, 5, 6. So this is our 6s. Then we go from 56 to 57. This is the 4f down here. So 4f, and we're 1, 2, 3, 4 elements into it. Now we do our orbital diagram. 1 orbital in the 6s, and then 1, 2, 3, 4, 5, 6, 7 in the 4f. We have 4 electrons. So we place 1 electron in each of the 4f, and we're going to have some empty ones. All right, that's it. Chemistry is easy, life is hard. And I lied when I said one more. I want to do another one because I really want to do one where we double up on something. So let's do another one. This time, let's do... I'm trying to avoid one that's going to violate a rule. Aha! Let's do iron. Here we are. The preceding noble gas to iron is argon. Read it like a book. We're at the fourth row here. S block, so 4s2. Then we're in the D block, and remember, D block is row number -1, so it's 3D. 1, 2, 3, 4, 5, 6. We draw our orbital diagram. 4s, 1, 2, 3, 4, 5 for our 3D. 4s has 2 electrons, then we put our electrons in our D. 1, 2, 3, 4, 5. All our degenerate orbitals have 1 electron in them. So now we can double back up. So that's iron. All right. So those are all examples of elements that follow the rule. We now want to look at some elements that are deceptive. It turns out there are 21 known elements whose electron configurations slightly violate what would be predicted from the periodic chart. These anomalous electron configurations can usually be explained by the desire of atoms to have half-filled or completely filled D subshells. Let's take a look at a couple examples. The first example that occurs on the periodic table actually occurs very early, and that's chromium. If you look at chromium, based on its position, you'd say that its electron configuration would be 4s, 1, 2, 3, 4, 5, 3d, and you'd say 4s completely filled, and it's 1, 2, 3, 4 into the D. This is what the periodic table predicts. It turns out, however, that it's very stable or a lower energy configuration. Remember, we do fall, even these exceptions follow our off-ball principle. They just violate from what we'd predict. Our chromium can create a more stable situation for itself if it garners a half-filled D subshell. Since chromium can't create or destroy electrons at random, or it can't ruin its electrical neutrality, what chromium does is it takes one of its 4s electrons and it moves it to the 3d. Therefore, the electron configuration for chromium is actually this, or if we were to write it in condensed notation, 4s1 3d 5. Chromium has extra stability by garnering that half-filled D subshell, and we'll see that repeated with several other elements. Nearly everybody, and I said nearly, everybody in that column is going to repeat that well, let me even retrace that. Molybdenum here, right below chromium, is going to wind up doing the same thing, moving one of its 5s electrons into the 4d because of that low energy overlap. Well, if half-filled d subshells are extra stable, I wonder what the situation is for completely filled d subshells. I bet they're super stable. Yeah, you figured it out. You called it right. There's extra stability when you have a completely filled d subshell. Let's take a look at some good friends. Those rare earth metals. Oh, those aren't rare earth metals, but your copper, silver, and gold. Let's just work with silver for a second. Silver, the preceding noble gas, is krypton. We have 5s2, and then we enter the 4d. 1, 2, 3, 4, 5, 6, 7, 8, 9. What's completely filled? 10, right? Our periodic table predicts this. However, you can see they're one electron away from completing the set. Right? If you've ever collected your cards, you know how maddening that can be. So what silver does is to complete its d subshell, it takes one of its 5s electrons and moves it to the 4d. So silver winds up with an electron configuration of winds up with an electron configuration of krypton 5s1 4d10. So it violates what would be predicted in order to complete that completely filled d subshell. Copper and gold are going to do the same thing. They're going to move a s electron into the d to complete that d subshell. Some elements are so extreme in their desire to have that completely filled or half-filled d subshell that they'll actually move multiple electrons around, as in they'll move 2 electrons around. The classic example of that is going to be right here, palladium. If we look at it, we'd expect it to be 5s2 4d8. Instead, palladium actually moves both of its 5s electrons into the 4d and winds up as palladium 4d10. You can find other examples of nonconformity. Most of these examples will occur in really large atoms, usually with atomic numbers greater than 40. Why is that? Remember, as you increase the number of the energy level, the energy difference between those energy levels decreases, so it's easier to jump ship between those energy levels. But those are examples of some anomalous electron configurations. I don't expect you to memorize all these anomalies. However, I've gone over 5 very common ones, and if I tell you an element is anomalous, I expect you to be able to predict, knowing that it's anomalous, why it's going to be anomalous, how it's going to be anomalous. In other words, if I told you you had a mysterious element that had an electron configuration of NS2 and a predicted configuration of ND4, what would his configuration likely be in reality if it was anomalous? I'd expect you to be able to tell me that NS1, ND5 was the likely result. We'll take a look at a couple examples here. Before we do that, would you kindly write down the word Vikings. Write down Vikings. I hope you're writing down Vikings. V-I-K-I-N-G. Vikings. Alright, to which element does the following orbital field diagram belong? This looks difficult, but we can do it in one of two ways. First, we could go to our periodic table. We could find the second row, P block, and move 2 over in it. And when we do that, we discover that it is the element carbon. Or we could say we have 2 electrons here, plus 2 electrons here, plus 2 electrons here for a total of 6 electrons. And in a neutral atom, it would be atomic number 6, or again, carbon, that would have that electron configuration. Alright, in order to write the electron configuration for tin, the first thing we have to do is locate it on our periodic. So let's see, where's tin? Here's tin. The preceding noble gas is krypton. So now we can read it like a book. 1, 2, 3, 4, 5. 5s2. 4d10. 5p2. So there's our electron configuration for tin. And let's see if we're right. And what do you know? We are indeed. One last thing is I introduced the term valence shell as your outermost shell. It should be noted that for main group elements, the group number with an A next to it tells you the number of valence electrons. All the elements in group 8A have 8 valence electrons. All the elements in group 7A have 7 valence electrons. Not only that, but all elements in the same group have the same electron configuration in their valence shell. Everybody in group 1A is NS1, and we went over that last lecture, but this is just a gentle reminder to you. And it also drives home that number of valence electron related to group number. 4A elements would have 4 valence electrons, 5A elements would have 5 valence electrons, so forth and so on. That's it.